Rotational equilibrium continued. So let's put here, we're still doing rotational equilibrium problems. And the idea here is that you have two equations. So one of them is the equation for torque, and that's distance from your axis of rotation to whatever the force is applied times the force F times the sine of the angle theta. Now, in case you forgot what this, it's good to visualize what's happening here. So if you have some kind of a board here and then you wish to rotate this board, you're going to apply a force F, but this force F is at a certain distance d from your axis of rotation. So here's your distance d, and then your axis of rotation goes here through this pivot point, and the angle theta is the angle between d and F. Now the other equation that you have is, for rotational equilibrium specifically, is the net torque. The sum of all of the torques is 0. And then there's a convention about positive and negative sign for the torque. So if you have, let's say you have a board and the board goes like this. Let's say you have the axis of rotation and let's say that the axis of rotation is here. So this is where you'd have some kind of a pivot set up, and this thing can rotate either this way or this way. Let's say you have a few forces acting on it. So let's put force like this, and then another force like this, another force like this, and maybe another force like that. So each one of these forces will contribute to a overall torque. Each one of these forces is going to generate certain torque, and each one is going to have it's going to be either positive or negative. So the convention is that if you get this kind of a rotation, right? Maybe I'll put it, see, let's say we have this coordinate system here, this is X and this is Y. If you have a counterclockwise rotation, then the torque is positive. If you have a clockwise rotation, then the torque is negative. And so, for example, this force here, let's do this force. If this was the only force acting on this bar, then the rotation of the bar would be counterclockwise. And for that reason, the torque produced by this force is going to be positive. So this would give us positive torque. Now, on the other hand, this force here, if this was the only force acting on a bar, then that force would give us this kind of rotation, and that would be a negative torque, right? If you get clockwise rotation, then that is a negative torque. So we're going to put here, this is minus. If this was the only force acting on a bar, then we would end up with rotation that looks like this, which corresponds to this one, right? Clockwise rotation, and that would give us negative torque. So this would be negative. And then finally, if this was the only force acting on the bar, then that would give us this kind of rotation, which corresponds to the counterclockwise rotation. And so, excuse me, this would give us a positive torque. So that'd be positive. This is a positive torque. All right, so that's all of the background. Now let's go ahead and solve some problems. I'm going to solve problem 6. And then you will do problem 5. That is going to be the assigned homework. And then I'm going to also solve problem 7, and that might do for us. So let's move this whole thing here. Let's look at problem 6. The picture is there. I'll redraw it anyways, but the picture's there. Number 6, it's on your worksheet. And let's just draw it. So what I have is this wall, then I have a bar that comes off of the wall, with some kind of a horizontal bar here that goes out, and then there's a rope, and the rope holds this whole thing and this whole thing together. So let's maybe do that, and I'm going to extend the wall a little. All right, and then somewhere here at this point we have this. Let's maybe put it here. We have this block, right? That sits here. And then this is a wall. All right, so this horizontal bar is in equilibrium, rotational equilibrium. It's not just in rotational equilibrium. It's also not accelerating up, down, left, or right. So it's just in equilibrium, translational and rotational equilibrium. Let's identify all of the forces that act on it first, and then we can actually look at the problem itself. So one of the obvious forces that acts on this bar would be the force of gravity. And gravity acts on the center of mass of the object, and center of mass of this object is going to be at the center of the object. So here's weight, and we're going to call it weight 1. Now there's also this weight here that is pulling on the bar. So what I'm going to do is, just looking at this mass itself, there's a weight here, and then there's a tension here. Now then, looking at the, and of course these two are the same, right? This tension is weight 2. Now looking at this bar here, there's tension pulling downwards on it, right? So there's tension that pulls down, and that tension is just this tension, and this tension is simply equal to the weight. So instead of having all of this here and making it look convoluted, what we should do, or at least what I'm going to do, is get rid of all of this. I'm just going to do this. From this point here, there's this weight that pulls down, and I'm going to label this as weight 2, and that weight 2 is simply, what was it? The little mass is 10 kilograms. So this would be 10 times 9.8 gives me 98 newtons, right? Because that little mass here was 10 kilograms. All right. Now I also have tension. So there's tension here, right? That's pulling in this direction at some angle. And we know the angle. We know the angle. The angle is 25. So let's put this here where this is 25 degrees. And there is another force. So we have this weight, we have this weight, we have tension, but there's another force. The wall itself is pushing back on this rod. But the direction in which this wall is pushing back is not going to be this. That wouldn't be true. The direction in which, so because of the pull of the tension, the bar itself is going to exert a force on the wall. I mean, that should make sense, that the bar itself, this bar here, is going to exert the wall, a push on the wall, because of the but there will be two components to it. Because of this rope here, this rope pulls, if you will, on this bar, and this bar pushes into the wall. But there's also this weight here that pulls down on it, and so there's also a drag down along the wall. So we have a component that is we have a component that is into the wall, and we have a component that is down the wall. So the resulting force of this bar on the wall is going to be the sum of these two, and so it's going to point like that. Now I'm going to clean this up. So at this point here, point of contact, the bar itself is pushing like this at the wall, which means that the wall itself is pushing in exactly with the exactly same force, but in the opposite direction. So the wall is pushing on the bar in this direction. Now exactly at what angle, I don't know. So I'm going to label this thing as some alpha. I mean, if this is alpha, if there's a lot of weight here, then this force is going to point a bit more vertical. If there's a little weight here, then this force is going to be more horizontal. So the exact angle is not known to me, but it's going to be at some angle. And I'm going to call this thing not the normal force because it is not perpendicular to the wall, but I'm going to call this thing the reactionary force, the reaction force, R. So there's this R, which is the reaction force. Reaction force. And the problem itself asks to calculate the tension and the reaction force exerted by the wall. So we want to find these two. All right, now let's put some more numbers on this thing. So the mass of the bar is 300 kilograms. If it's 300 kilograms, then I can calculate this weight here. Let's move this a little to the left. So 300 times 9.8, let's see what we get for that. So this weight 1 is 300 times 9.8. $29.40 is what I have. So I'm going to put here, this is 29.40 newtons. Okay, so I have this, I have the angle, I don't know tension, and I don't know R. All right, so I can go ahead and start to solve something about this. I can now start to find some of these things. So I know that the net torque is 0, right? The net torque is 0 because the bar itself, the horizontal bar, is not rotating. But that means that the sum of all of the torques is going to be 0, and so the torque produced by R plus the torque produced by weight 1 plus the torque produced by weight 2 plus the torque produced by tension, all of these will give me 0. The only thing is that in order for me to use this expression here, this equation, I have to have, well, torque is always in reference to some axis of rotation, to some point. So I have to determine where my pivot is, right? Because remember, torque is force times distance times the sine of the angle theta, and this distance is d, is the distance from the pivot or the axis of rotation to whatever the force is applied. So you can think about it for a bit. Where should I put the pivot? Where should I put the pivot? Well, you could put it anywhere you'd want to, but that doesn't mean it's going to, that would make your life easier. I mean, if you put your pivot here, you could do that, and then you'd say that this is where I'm going to calculate all of the torques relative to the axis that goes through that point. And so you could do that. You could, figure out this d and this d and this d and that d and all the angles, but I wouldn't really get you far. You want to be clever about this. So what we'll do is we're going to put pivot right here. And the axis of rotation is going to go through that point. By doing that, I get rid of the torque produced by R, because the torque produced by R about this pivot point is going to be 0. So, and then the only unknown left is T. Right, so what I can do now is torque produced by R, 0, because any force applied at the axis of rotation is going to give me no rotation. So I'm going to get no torque. Now, at the same time, the signs, I have to pay attention to the signs. So the sign by torque produced by this force here, this is going to be a negative torque, because that's going to give me this kind of rotation. So that's going to give me negative torque. So that's minus. This is going to give me this kind of rotation. So it's also going to be negative torque. So this is negative torque. And then tension, if tension were the only force acting on this bar, then I would get this kind of rotation, and that's a positive torque. So this should be plus. All right, so now I'm good. Let's substitute whatever I can. So torque produced by weight 1, that would be 2940 negative times, I need the distances. All right, so how long is this bar? This bar is 10 meters long. If it's 10 meters long, then that means that I have, see if I can use this color. That means that I have 5 meters this way. So I have 5 meters this way, and I put here times 5 times the sine of 90, because this is at 90. Okay, so that's settled. Minus second torque is 98 newtons times however far this force here is. So I need that distance. So let's see what that was. So this little mass is 0.8 meters away from the end. So if it's 0.8 meters away from the end, then that means that this is 9.2 meters. So times 9.2 times the sine of 90, because I have 90 degrees here, and then plus T, I don't know what tension is, I'm going to use T, times 10, because tension is 10 meters away from the pivot, times the sine of the angle between distance D and T. So I'm going to put here sine of 25. All of that equals 0. So sine of 90 is 1, sine of 90 is 1, and then when I run this thing through, I can easily calculate for T. So T equals, let's see what that's going to be. So I get 3691 newtons for tension. 3691 newtons for tension. It's actually 92 newtons. So that's tension. All right, so that's half the problem. Now the other half of the problem is finding R. I can't just put pivot at this location and now try to calculate For R, because I don't know this angle alpha, like alpha is unknown to me, so I would have two unknowns. If I were to put pivot here and then figure out all of the distances to all of these forces and run this thing through, the net torque equals 0, then I would still have two unknowns because I'd have this angle alpha and R. So I can't do that, but I can do something else. I'm going to redraw the bar here. So here's the bar. And I'm going to redraw the forces. So I have the tension. And I have R. I have this weight and I have this weight. And now this one here is 2940. This one is 98. This tension is 3692. And this tension has the X component and it has the Y component. Right, so there's Tx and Ty, and I can calculate this out. So Tx would be 3692 times the cosine, nope, times the sine. Yeah, actually times the cosine. So the X is with the cosine, times the cosine of 25. All right, because here's where I have 25 degrees, so I can find Tx, this is Ty. And you put here Ty is this one, Tx, that's this. And then this here is just T. So I can calculate Tx, I can calculate Ty. I will need this stuff, 3692 times the sine of 25. Let's see what this is. All right, so Tx is 3346 and Ty is 1560. Now, if you look at this here, and then this is R. So this is R, which is what I'm after. I want to figure out what this R is. I also have the X and the Y components of R. So here's Rx, put here Rx, and then here's Ry. Now the bar itself is not moving left and it is not moving right. So the bar itself is not moving left, nor is it moving right. That means that the forces in the X direction have to cancel out. So Rx must be equal to Tx. If that was not the case, so for example, if Tx was bigger, right, and then note that Tx is right here. This is Tx, Tx is pointing to the left. If this Tx was bigger than Rx, and this is Rx, then the bar would sway to the left. If on the other hand, Rx was bigger than Tx, then the bar would sway to the right, but they don't. So Rx must be equal to Tx. And so I have, that's 3346 newtons, right? I pull this thing from here. All right, now along the Y, right, the bar is not moving up and it is not falling. So all of the components, all of the force components along the Y must cancel out. Now I have two components that point up. So Ry plus Ty, these are the two components that point up. And then I have two forces that point down, and that would be the two weights. So 2940 plus 98. Right? These two added together, which point up, must be equal to these two added together, which point down. They have to cancel out since the bar is not moving up and it is not moving down. So I can now go ahead and finish the problem. Since Ty is known to me, that's 1560. I pull this one from here. And this is equal to 29. Oh, I guess I can just add this up. So let's see, what do we have? 2940 plus 98. So this is 38. 3038. And then I can of course subtract this, and so now I'm going to have Ry equals, let's just run this thing here, 1478 is what I have. So 1478 newtons. Okay, so now what I have is I have Rx, right? That's this. And I have Ry. I'm going to slide this screen here. When I combine these, this green is bright. It's too bright. So when I combine these, that's better. Rx and Ry, I can now get R, right? Because I just found that the R is Rx 3346, comma Ry 1478, and that actually does it. This is an expression for R and just a vector notation. But if I want the magnitude of this, then I would have to do Pythagorean theorem, right? So 3346 squared plus 1478 squared, and then this whole thing, square root of it, and that will give me R being, well, let's run this thing through, see what we get. So 3658 is what I see here. 3658 newtons is R, and now I have solved the problem. So I found the reaction force, and I have found the tension. Right, so the problem takes a little bit of work. It's not a very difficult problem, but it does take a little bit of work, right? We have just found R and T. Now going back to this thing here. So problem 6 is what I solved. Is that actually, I'm looking at the answers. Let's see if we got the same answers. 3692, 3692, and 3658. Is that what it was? 36, look at us. All right, so I worked out. That's good. It doesn't always work out, but it did this time. So check here. We did problem 6 here, and now yours is going to be problem 5. Now problem 5 is going to be the same as problem 6, but I changed the numbers around. So if you follow for problem 5, as long as you follow the method that I gave you here, then you should be all set. You should get the correct answers. You can pause the video now and try problem 5 and then submit it as a homework assignment, but I'm going to move on to number 7. So now I'm going to solve problem 7. So I'm going to redraw this. Let me see how much room I have. I have plenty of room. Okay. So I'm going to redraw this thing. Oh, actually, do I need to redraw? Maybe I don't have to redraw it. Maybe I can get away. I should probably just redraw it. All right, so for problem 7, I have a wall. Then I have a floor. And then there's this ladder here. And let's use a line, straight line. So we have a ladder. And the ladder just sits like this. Now, I'm going to assume I probably have the angle. And the angle is 40 degrees. Okay, so this one here is given to me. This is 40 degrees, and I should probably give some thickness to it. I don't think it's, not that it's necessary, but let's just do it. All right, so here's the ladder there. And this thing is resting. I have no friction on the wall, so I'm going to put here no friction. That's a little unrealistic, but this is the case. I have no friction on the wall. And before I start calculating anything and trying to figure out what the problem is asking me to do, let's first determine this is a floor and this is a wall. Let's first determine what are the forces acting on this ladder. You can pause the video for a second and try to figure this out yourself. I'm gonna go ahead and I'm gonna start listing the forces. The obvious one, I think, is the weight of the ladder itself. There's a weight that pulls this thing down, so I'm gonna put weight here. And I can calculate this, I think, because the ladder is 50. Yeah, so the ladder is 50 kilograms. That implies that the weight here is 490 newtons. So the weight is 490 newtons. Then I have this reaction force here from the ladder is not sliding, so there's no sliding. That's important. Let's put this here. No sliding. Everything is nice and static, no sliding. So what I have is, how should I do it? I can, two ways of doing it, I guess I could. It's always, the simpler the better, is always the case. So maybe what I'll do is the ladder is pushing into, the ladder is pushing at the floor and the floor is pushing back up, so there's a normal force. But at the same time, there's some friction here, right? There's definitely, if there was no friction here between the ladder and the floor, then the ladder would necessarily fall. And so it would just have to slide. So there's a friction there, and that friction is prohibiting this ladder from moving in this direction. Because if we remove friction, the ladder goes in this direction. So that means that the friction always opposes motion. So friction itself, the frictional force, static friction, is going to point in this direction. So here's the static friction, force of friction. Right, so there's normal force because the ladder is pushing on the floor and then the floor is pushing back up, and there's also this the force of static friction that pushes this thing to the left, I suppose. It just maintains it in a static state here. Now on the other hand, here what I have is, so normally I would also have the ladder is pushing into the wall and the wall is pushing back on the ladder, so I should have this normal force. I'm going to put here, this is N. Now the two N's are different, so I should label this as N1 and I should label this as N2. And normally what I would have is a frictional force here as well. Since the ladder would be falling down, there's got to be a frictional force that points up, so you'd have force of static friction. But the problem says that there is no force of friction, so we're going to get rid of it. It's not there, we're ignoring it. The wall is frictionless. Alright, so then these are all the forces that I have. And now let's see what am I to calculate here. Find normal force exerted by the wall. Okay, so this is one of the unknowns. And find the normal force exerted by the floor. This is the other unknown. And the frictional force between the ladder and the floor. So this is the third unknown. So I have three unknowns, N1, N2, and the force of friction. And let's see, is there anything else given to me, or is that it? Oh, the length is 3 meters. So I have the length, the whole length is 3 meters, and so on. Okay, now no sliding, no rotating, nothing is happening here. That implies that the net torque is 0, and also that the net force is 0. But let's go off of this one first. So the torque by all of these forces is 0, then torque by N2 plus the torque by weight plus the torque by the force of friction plus the torque by N1. All of this is 0, but I can't go any farther until I determine where my axis of rotation is. Once I have that, then I can determine my distances and I can actually calculate these torques. So where should I put my axis of rotation? Where should I put my pivot, and so that I can actually measure the distances too? Well, you have to be clever about it, and there's really, I mean, there are two I think obvious candidates. It's either you either want to put your pivot here at this location on the floor or here, and either way you would get to the answer. It's just that one way is maybe faster than the other, although I'm not really sure that's the case. Not sure if any one of the methods is any faster, but what I'm going to do though is I'm going to say, let's do this. Let's put a pivot here first. So I'm going to put pivot here. Through this point, the axis of rotation goes, and I'm going to measure my distances to this specific point. What that does for me is it gets rid of the torque produced by this N and this F, because any force that is pushing on the axis of rotation is going to generate no rotation. So this one goes away, and this one goes away. I only have to worry about these two torques. All right, now the torque produced by, I need a couple things before I move farther. I need the angle. So if this here is 40 degrees, then this here is also 40 degrees. So let me extend this out. This here is 40 degrees as well. And if this is 40 degrees here, then this is going to be, well, shouldn't be too difficult to see. If this is 40, then this must be 50. So you have 50 degrees here, right? 50 plus 40 gives you 90, 90 plus 90 gives you 180. Okay, so now that I have all of that, I also need the distances. Let me see if I can find, I want a better color on this one. For the colors, let me just put this there. Okay, so torque produced by N2, well, that would be N2 times however far away N2 is from the pivot, and that would be 3 meters because the bar is 3 meters. So this is going to be times 3, and then times the angle between distance d. All right, so now let's draw this distance d from the pivot all the way to wherever the force is applied there. That's distance d, and that's 3 meters. This whole thing is 3 meters because the bar is 3 meters. So I'm gonna put this, oh, I already have it. So N2 times 3 times the sine of, well, what's the angle? Angle is 40 degrees. The angle between D and the force N is 40 degrees, so it's a sine of 40. I still have to figure out the signs, like plus, minus, but for the moment, let's just keep it here. Plus the torque produced by the weight, so that would be 490 newtons times, well, now my story ends. You know, it's the distance is now from the pivot to the weight, which is halfway. So that's that, and that halfway would be 1.5 meters. So this is 1.5 meters because the whole length of the bar is 3 meters. So this is 1.5 times 1.5 meters times the sine of the angle between D and the weight, and that would be 50. The angle here is 50, so sine of 50 and all of this equals 0. So let's slide this just a little bit, equals 0. Okay, the signs, plus, minus, which torque is which. So if the, here, if this is my pivot, right here, this is my pivot. If this was the only force, this weight was the only force acting on this bar, then the bar would necessarily move like that, and that's going to give me a counterclockwise rotation, which is a positive torque. Yeah, it's a positive torque. So then this is plus, this is plus, and this remains as plus. And then if the only force acting on this bar was this normal force, then I would get clockwise rotation, right? And a clockwise rotation corresponds to the negative torque. And so negative torque for N. N is minus, N is minus. Now I have the signs right. So the only thing that is unknown here is N2. I can easily calculate that. Let's figure out N2. So this is 292 newtons is what I have. All right, so N is done. Now to figure out the other two forces, right, I still have to find N1 and F. You really want to use this now. F net equals 0. You want to use that. The reason being is that by looking at the picture here, it's pretty clear that this ladder is not moving to the left and it is not moving to the right. Like, it's just not sliding in this direction, it's not sliding in that direction, it's not sliding at all. So all of the forces that point to the right must be equal to the forces that point to the left. Now what forces point to the right? Well, here's a force that points to the right, N2. What's the force that points to the left? Here's the force that points to the left. So the two must be the same. So N2 must be equal to the force of friction. And so of course that means that I have just found the force of friction. It's 292 newtons. Also, this ladder is not moving down, its center of mass is not moving down, its center of mass is not moving up, and so all of the forces that point down must be equal to all of the forces that point up. Now what forces point down? Well, here's the force that points down. It's this weight here. And what's the force that points up? It's this normal force. So they must be equal. So I'm going to put here on the bottom that the weight must be equal to N1. And if that's the case, then I just found N1. That obviously is 490 newtons. So 490 newtons, and that does the trick. I'm gonna do this. Now the problem is solved. So, all right, make sure you're comfortable with this problem. Try to solve it once or twice on your own, and then just consult the video here. But your homework and what you will submit is this problem here, problem 5, and that should do.